Hello, this lesson rather, we'll talk about how to prepare a buffer solution. So now going back to the last lesson, we learned that a buffer solution is one that contains a weak acid or base along with its conjugates, base or acid respectively. So a solution of a weak acid and a salt containing the conjugate base of that weak acid, or it could be a solution that contains a weak base and a salt that contains the conjugate acid of that weak base. So key thing being this solution needs to have both components to be a buffer. So you can do this two ways, one of two ways. First, it says buffers may be prepared by mixing an equal number of moles of weak acid and a conjugate salt of the weak acid, or equal number of moles of a weak base in the conjugate acid of that weak base. So now technically it doesn't have to be equal moles as long as we have a good amount of both the weak acid and its conjugate base, or the weak base and its conjugate acid. So that's one way of preparing a buffer. The other way is through partial neutralization. You take a weak acid and you neutralize some of it. In neutralizing some of it, that solution will still contain some of the weak acid, but it'll also contain some of the conjugate base produced from that partial neutralization reaction. Now, something very important, we'll talk about this more later, but we'll introduce it now. When equal amounts of the weak acid and conjugates are present, or weak base and its conjugate are present, for an acidic buffer, the pH of that solution will be equal to the pKa of the acid. I'll show you why later. Likewise, for basic buffers, the pH equals the that should say pOH. So cross that off, right? It's pOH equals the pKb of the weak base. All right, let's take a look at an example where we're determining the pH of a buffer solution. So 19.5 on 751. It says calculate the concentration of H plus and the pH of a buffer solution prepared by mixing 200 milliliters of 0.10 molar sodium fluoride and 100 milliliters of 0.050 molar hydrofluoric acid. Ka for hydrofluoric acid is 7.2 times 10 to the negative fourth. All right, so something important to keep in mind here is that you're mixing these two solutions, and we're going to assume that these volumes are additive. So we need to determine the concentrations of HF and F minus. We don't care about the sodium from sodium fluoride. The F minus, the conjugate base of hydrofluoric acid. So take a look in the solution. Basically, this is a dilution calculation, so we're determining the concentration of HF and F minus after the solutions have been mixed, but before any type of reaction can occur. So the book here is using millimoles. So we got pretty small quantities of chemicals. So take the volume times the molarity. If you keep that volume in milliliters, volume times molarity will give you millimoles. You can take millimoles of each substance and divide by the total volume here, which is 300 milliliters, and we get our concentrations of HF and NaF. So for the HF, it's 0.017 molar after the solutions have been mixed, and the fluoride is 0.067 molar. Now, if you turn the page in the book, they're going to run through this calculation using Ka, but of course we have a buffer, so you're more than welcome to use the Henderson-Hasselbalch equation. So we have pH equals pKa. So we take the negative log of the Ka, and that'll give us the pKa, plus the log of concentration of F minus over concentration of HF, and that should get you your answer. So I encourage you to try it out. Try it out using the Henderson-Hasselbalch and see if you get the same answer, the answer being 3.74 for the pH. All right, go ahead and try number 37. A little different problem. In this particular problem, you're not calculating the pH. So the pH of the solution is given to you, and you're looking for one of the concentrations, either the concentration of the weak acid or its conjugate base. In this case, specifically, we're looking for the concentration of the benzoate ion, which is the conjugate base of benzoic acid. So you can see the chemical formulas there. Benzoate has one less H plus than benzoic acid, so that means it is a base. Go ahead and pause the video and set that up, and we'll check in a minute. All right, so here's our setup. The Ka of benzoic acid, 6.3 times 10 to the negative fifth. I'm solving for X here, which is the concentration of the conjugate base for benzoic acid, benzoate. And so take the negative log of the Ka and then subtract that from the pH. And then we need to get rid of that log. So anti-log both sides, so 10 to the X, 10 to the whatever's on each side. That'll get rid of this log, and you'll have X over 0.045 equals some number. And solve for X, we get 0.36. Let's put in some units there. So the answer is actually 0.36 molar is the concentration of benzoate. All right, a little different problem. Take a look at 19.6 on 752. It says a solution is 0.10 molar in aqueous ammonia. Calculates A, the number of moles, and B, a better calculation, the number of grams of ammonium chloride that must be added to 500 milliliters of the solution to prepare a buffer that has a pH of 9.15. Says you may neglect any volume change that occurs after adding the solid ammonium chloride to the solution of aqueous ammonia. All right, so again, let's set it up. You can use Henderson-Hasselbalch if you want. They use, of course, Kb here. And so if you use Henderson-Hasselbalch, once again, we're going to calculate the concentration of the conjugate acid this time, NH4 plus. And then once we get the concentration of the NH4 plus, we can use that along with the volume of the solution, which is 500 milliliters, to find moles of NH4 plus. Keep in mind there's a 1-to-1 ratio between NH4 plus and NH4Cl. Once we have moles of NH4 plus or moles of NH4Cl, we can use that to find grams of NH4Cl, which in this case is 3.5 grams. So to make a buffer that has that pH, you would take 500 milliliters of your 0.1 molar aqueous ammonia solution, and to it add 3.5 grams of ammonium chloride. That would give you enough ammonium ions in solution to make a good buffer, a buffer that has a pH of 9.15. All right, go ahead and try one out like that. I think it's pretty much the same type of problem, number 39. We're trying to find the mass of ammonium chloride. Actually, no. So the question asks for concentration of ammonium. Let's take it a step further. Let's say you make a 100 milliliter buffer solution. So instead of calculating just concentration of the ammonium needed to make this buffer, that's a pH of 8.70. Let's say you wish to make 100 milliliters of this buffer solution. How many grams of NH4Cl would be needed to make this solution? Go ahead and pause the video and set that up. All right, so here's our setup. So notice that you're given the pH of the solution, but this is a basic buffer, so we need to find the pOH. So took that pH, subtracted from pKw to get to the pOH. Kb for ammonia, 1.8 times 10 to the negative fifth. Again, I'm solving for concentration of the conjugate acid, ammonium, which happens to be 0.27 molar. So if we look at our dissociation equation, keep in mind you can't just have ammonium. That ammonium comes from somewhere. So that comes from ammonium chloride. So we have a 1-to-1 ratio of ammonium to ammonium chloride. And so I kind of just set it up in one shot here at the bottom. So take the concentration of ammonium times the volume of the solution. I said let's make 100 milliliters of solution. That'll give us moles. I guess I could have done millimoles too, which would have been fine. Moles of ammonium, and then I applied my mole ratio here. and then converted that to moles of ammonium chloride to grams. And so you would take 100 milliliters of your 0.075 molar solution of aqueous ammonia, and to it add 1.44 grams of ammonium chloride. All right, take a look at another problem, 19.7. Calculate the pH of a solution obtained by mixing 400 milliliters of 0.200 molar acetic acid solution and 100 milliliters of 0.300 molar sodium hydroxide solution. So on this one, you actually probably want to set up a SCAR table. And let's write the equation for the reaction between the acetic acid and sodium hydroxide. Once again, I'm going to leave out the sodium. It's just a spectator ion. And so what we end up with then is, let me make sure I got this right, CH3CO minus and some water. And again, we want to deal with moles of each substance. The book uses millimoles, I believe. So we'll do that. That's fine. So take 400 milliliters times 0.200 molar, and you get 80 millimoles of acetic acid. And then 100 milliliters times 0.300 molar sodium hydroxide, that is 30 millimoles of hydroxide. We have none of this. We don't care about that. So again, notice that the limiting reactant is hydroxide. Everything, of course, again, in a 1-to-1 ratio. And notice that we have a solution that contains both acetic acid and its conjugate base. If we want to calculate concentrations of each of those, if you're going to use Ka, you need to calculate concentration. If you're using Henderson-Hasselbalch, technically you don't. But take those and divide by the total volume, which was 500 milliliters. So millimoles divided by milliliters equals molarity. That will give you the concentrations of both the acetic acid and acetates. Book shows actually using Henderson-Hasselbalch here, so plug in our values, and you should be able to get the pH from that. And so we get 4.52 is the pH of that buffer solution. All right, so go ahead and try one like that. There's not a space really in it in the notes for it, so just below example 19.7 or anywhere in the margin you have there, do number 35 on page 35 on page 765. Go ahead and pause and do that now. Sorry, I should have told you just to do the first part. That's all we're worried about here. So we have a 1 liter solution. You have sodium nitrite and hydrochloric acid. All right, so what's going on here? This time we have nitrite, which is the conjugate base of nitrous acid, reacting that with hydrochloric acid. So make sure you get the right equation here. And so this reaction produces nitrous acid. We get moles. These are moles. It's in a 1 liter solution, so that's also our concentration. And then I use the Henderson-Hasselbalch pKa of nitrous acid, 3.35, log of, be careful to put these numbers in the right order, conjugate base, 0.045 molar, over concentration of the acid, 0.070 molar, and we get a pH of 3.16. All right, that concludes this lesson. Next time we'll be talking about indicators and titration curves and titration calculations. Thanks for watching.